If you were gasping for oxygen, would you start ripping apart water molecules just to get it? Probably not. But you know who would? Your citric acid cycle.
Ketogenic diet has neurological benefits. Why do we have to eat such an enormous amount of food?
Complex science, clear explanations. Class is starting now.
Let's face it, if you're starving for oxygen, you're not going to start inhaling water. That's called drowning. But your citric acid cycle, every time it turns, a turn of the cycle uses water to rip it apart and harvest its oxygen. Now, I'm not saying you suck. I'm just saying your citric acid cycle is cooler than you. But that's okay. I can't do this either, and my citric acid cycle is way cooler than I am. The point I really want to drive home here, though, is we need to understand the relationship between needing enough oxygen to release carbons as carbon dioxide and getting that oxygen when we don't have enough from water. If we begin to understand that in the context of the citric acid cycle, it lays the foundation for later looking at why fats and carbohydrates, because of their different oxygen content, require different amounts of water for their metabolism and release different amounts of carbon dioxide during their metabolism. That's important to so many different issues because carbon dioxide, for example, puts more stress on the lungs. On the other hand, it helps with the delivery of oxygen to tissues, and it supports certain actions of vitamins, like the functions of vitamin K. So we can later talk about why that would make us want to shift the fat and carbohydrate in our diet according to our different goals. But for now, let's master the basic fundamentals of this concept in the context of the citric acid cycle. You can see on the screen that the acetyl group, shown on the left, only has one oxygen atom, and yet it has two carbon atoms. By contrast, the carbon dioxide molecule on the right has one carbon atom and two oxygen atoms, the total reverse. This is reflected in their empirical formulas. C2H3O, one oxygen for two carbons. For carbon dioxide, it's CO2, two oxygens for the one carbon. What that means is that the acetyl group does not have enough oxygen to release its two carbons as carbon dioxide. Two carbons will make two carbon dioxide. Two carbon dioxide will have four oxygen atoms. We only have one oxygen atom in the acetyl group, and that means that we are in need of three additional oxygen atoms. As you can see on the screen, water and phosphate can both be sources of oxygen. Water has one oxygen as H2O, and phosphate as PO43- has four oxygen atoms for each phosphorus atom. What we'll see is that water is the ultimate donator of all three oxygens that need to enter the citric acid cycle during each turn of the cycle. But phosphate plays an important role in transferring one of those oxygen atoms into the cycle. When we first started talking about the citric acid cycle, we saw this two-step reaction of the condensation of oxaloacetate with acetyl-CoA to produce citral-CoA and the hydrolysis of citral-CoA to form citrate. At the time, we pointed out that citric acid, or citrate, has three carboxyl groups, and the hydrolysis of citral-CoA by donating an OH group, constitutes that third carboxyl group. Now we can look at this exact same set of reactions, and we can say that the hydrolysis of citral-CoA to form citrate donates the first oxygen atom that we need out of 3, and that is the exact same oxygen atom that got donated to constitute the third carboxyl group. The second oxygen atom out of 3 is supplied by phosphate, but it actually is ultimately derived from water. And in order to understand this, we need to look at ATP hydrolysis in a little bit more detail. Shown on the left is adenosine triphosphate. During ATP hydrolysis, an OH from water goes to one of the phosphates that breaks off, and the H gets left in solution. And the reverse of hydrolysis is always going to be dehydration synthesis. So if we're going in the opposite direction to resynthesize ATP, the OH comes from the free phosphate and a hydrogen ion comes from solution. Together they make water. Water leaves and ATP is formed again. Now, let's look a little bit more deeply at the structure of the phosphates. We said before that every phosphate has 4 oxygen atoms. But if we look at the ones in ATP, if we look very superficially, we can kind of fool ourselves into thinking that that's the case. We look at this phosphorus and it's attached to 1, 2, 3, 4 oxygen atoms. This phosphorus is attached to 1, 2, 3, 4 oxygen atoms. And this phosphorus is attached to 1, 2, 3, 4 oxygen atoms. So far, so good, right? But look a little bit more closely and try to account for all the oxygen atoms. This terminal phosphate, if we count it as having 4 oxygen atoms, we've already counted the one that it's sharing with the second phosphate. If we don't count it again, we'll say the second phosphate has 1, 2, 3 oxygen atoms. That's 3 instead of 4. And if we count that 4th oxygen atom as part of the second phosphate, we can't count it as part of the first phosphate. And so the first phosphate only has 1, 2, 3 oxygen atoms. So what we can say then is that phosphates in their bound state have 1 fewer oxygen atom than in their free state. And in any string of phosphates, only the terminal phosphate, because it's not bound to anything else on one side, is the phosphorus that actually has 4 oxygen atoms. If we look at the free phosphate over on the right, it has 4 oxygen atoms. And we look at the terminal phosphate of ADP, and it has 4 oxygen atoms. So what that means is that by taking a free phosphate and binding it into a string of phosphates, we're removing 1 oxygen atom as water. Therefore, ATP hydrolysis can be seen as a way of taking the oxygen from water and storing it in the free phosphate until it gets removed again during dehydration synthesis to connect that phosphate back into the string of phosphates to make ATP. To summarize, during ATP hydrolysis, an oxygen atom from water is stored in the free phosphate. Previously, we talked about how the formation of succinate from succinyl-CoA releases the enormous amount of energy in the thioester bond and transfers it to ADP to make ATP during what's called substrate-level phosphorylation. If we look at how this happens in more detail, we can see how this allows the oxygen atom that a free phosphate had taken from water to get donated as the second oxygen atom that needs to enter the citric acid cycle to release 2 carbons as carbon dioxide. What's happening overall in the first part of the reaction is that free phosphate is switching places with CoA. if we look at the organic chemistry of how this happens in slightly more detail, what we see is that the oxygen atom of the hydroxyl group comes in to bond to the carbon. And that's because oxygen atoms are electronegative, carbon atoms are not. This has a partial positive charge, this has a partial negative charge. They're attracted to one another. If it comes in and shares a bond with carbon, carbon now has 5 bonds, and that can't stay that way. So the 5th bond that carbon has with the sulfur of CoA will move on to the sulfur atom. So that electron gets donated from carbon to the sulfur. The extra electron on that sulfur allows it to be free, and it attracts the hydrogen to itself, generating free CoA and allowing succinyl phosphate to exist alone. We can already see that the oxygen atom of phosphate shown in pink is now part of succinyl phosphate. What we'll see in the next step is that that oxygen atom stays there. To look at it in a little bit more detail, the succinyl-CoA synthetase enzyme that's catalyzing this reaction has a nitrogen-bearing ring. When we saw thiamin's properties, we saw that that nitrogen in its ring structure had the ability to go back and forth between neutral and positively charged in order to facilitate the transfers of electrons. This nitrogen has similar properties. And so what happens is that the nitrogen comes in to bind to the phosphate, and it donates an electron to the phosphate. Now the phosphate has too many electrons, so it donates its electron to the oxygen. By donating the electron to the oxygen, now the bond is freed. The electron stays on the oxygen becomes negatively charged, and succinate is now self-sufficient. Instead of sharing a bond with that oxygen, that phosphorus is now sharing a bond with the nitrogen. That phosphate has been transferred on to the nitrogen-bearing ring of the enzyme. That enzyme passes the phosphate onto ADP to make ATP. You can see that as the electron moves towards the phosphate to form this bond, the nitrogen has a positive charge. As the phosphate moves off the enzyme to ADP, that positive charge disappears. This movement of phosphate to ADP to make ATP is what we refer to as substrate-level phosphorylation. But in the process, the oxygen atom from that phosphate has stayed on the succinate molecule. Usually when we form ATP during ADP phosphorylation, we have a dehydration synthesis reaction. We don't have that here because we've already removed the oxygen from that phosphate to put it on succinate. So this substrate-level phosphorylation isn't just unique because it's a rare example of synthesizing ATP outside the electron transport chain because we need to transfer the large amount of energy. It's also unique because it's one of the few places where synthesizing ATP doesn't release an oxygen to make water. Instead, it leaves the oxygen back on succinate. So in net, what has happened is that for some other purpose, the energy from ATP was utilized, and during hydrolysis of ATP, oxygen went from water to the phosphate molecule. That phosphate molecule donated the oxygen to succinate in this reaction, and then it goes back on to ADP, making ATP without generating water. That means an oxygen from water has been irreversibly consumed in order to put that oxygen on succinate, even though directly it's not coming from water, it's coming from phosphate. At this point, we've produced succinate and we've added the second oxygen atom out of the 3 that need to be added. The remaining 3 reactions of the citric acid cycle have 3 goals in mind. Number 1, we need to supply the 3rd oxygen atom that we established we needed at the beginning of this lesson. Number 2, we've lost our alpha keto group, that alpha ketoglutarate head. Remember that the alpha keto group is what allows a citric acid cycle intermediate to interconvert with amino acids. We need to reconstitute the alpha keto group so that we can allow the interconversion of citric acid cycle intermediates with amino acids again. And number 3, we need to leave the final citric acid cycle intermediate in a position where it's relatively electron deficient so that it's hungry to bind to something else. And that is what will allow it to bind to acetyl-CoA to initiate the next turn of the cycle. The first of these 3 steps is catalyzed by succinate dehydrogenase, and it's the oxidation of succinate to form fumarate. If we look at the succinate molecule, we've decided that we need to add an oxygen in the form of water, but where are we going to add it? All 4 carbons have all 4 binding sites full. We have no double bonds, meaning no electron deficient states. So what we do is we oxidize succinate to fumarate, and that is what is going to allow an electron deficient state that can accept additional atoms, including the 3rd oxygen atom. So the oxidation of succinate to fumarate is a way of preparing the molecule to accept the donation of the 3rd oxygen atom from water. We can see what happens here is that 2 hydrogens and their corresponding electrons are removed, loaded onto FAD to make FADH2. FADH2 will deliver those hydrogen ions and electrons to the electron transport chain to derive their energy to make ATP. Meanwhile, each of these carbons is now missing an electron, and so those carbons fold back on themselves to make a second bond with each other. Remember that the presence of hydrogens indicates the presence of an electron that's binding that hydrogen to the carbon. The absence of hydrogens and the presence of double bonds reflects an electron deficient state because the carbons are not bound to enough other things that they need to make additional bonds with each other to compensate. Because fumarate is in a relatively electron deficient state, it now has the ability to accept water. It does so in the hydration of fumarate to form malate, which is catalyzed by fumarase. And these 2 carbons, which had held hydrogens before, now have an OH and an H added by water, and one of those carbons just gets a hydrogen like it had before, but the other carbon gets an oxygen atom. That oxygen atom is the 3rd oxygen atom that needs to be donated to the citric acid cycle in order to release 2 carbon dioxide. So we've fulfilled goal number 1. We've added the 3rd oxygen atom. Now we need to look at why we need to reconstitute the alpha keto group. When we had alpha ketoglutarate before, we called it alpha ketoglutarate because the functional group we cared most about was the carboxyl at the top. And so we said that the keto group on carbon number 2 is alpha to that carboxyl. We got the alpha keto group in the first place because beginning with aconitase, we converted citrate to isocitrate and moved the OH group from the 3rd carbon to the 2nd carbon. Then with isocitrate dehydrogenase, we oxidized it to form the alpha keto group. Remember that the alpha keto group is what allowed us to have an exit point to form glutamate and to allow glutamate to enter the citric acid cycle because the alpha keto group can be swapped out for an alpha amino group to to make an alpha amino acid. But look what happened during the formation of succinate. We can look at the conversion of alpha-ketoglutarate to succinyl-CoA in NET, because remember, this was a very complicated multi-step series of reactions. But in NET, what happened was we removed the carboxyl group from alpha-ketoglutarate and just left the rest of the molecule as the succinyl group of succinyl-CoA. Now we have not a keto group, we have a carbonyl group, but it's not bound to another carbon, so it's not a keto group. We have the acyl group that corresponds to succinate, and when we, in this case, not hydrolyze, but when we phosphorylize the succinyl-CoA to form succinate, we add the oxygen that reconstitutes a carboxyl group at the top. So what we've done is, after we removed one carboxyl group, we borrowed this oxygen atom to make another carboxyl group. But now we don't even have the oxygen atom that we need to have an alpha keto group. Never mind the fact that there's nothing in the alpha position. So we can review the steps that we just looked at as a means of fulfilling goal number 2, reconstitute the alpha keto group. We have succinate, we oxidize it to fumarate, and that allows us to accept water in the next step. Accepting water during the hydration of fumarate to malate puts a hydroxyl group in the alpha position. And so at least we have the oxygen that we need in the alpha position, but it's not yet a keto group. The last reaction of the citric acid cycle is the oxidation of malate to form oxaloacetate, catalyzed by malate dehydrogenase. And this is the reaction that makes the final step in the reconstitution of the alpha keto group. What happens is that NAD+ oxidizes the second carbon and its associated oxygen. From the OH group, we take a hydrogen and the electron it shares with that oxygen. And from the carbon, we take the hydrogen and the electron that it shares with the carbon. That turns NAD+ into NADH with a free hydrogen ion, and those hydrogen ions and electrons will now be carried by NADH down to the electron transport chain, and their energy will be used to make ATP. This is the final step in which we harvest electrons from the citric acid cycle. But it also converts the OH group on the second carbon to a keto group. And that's because we've taken an electron from the oxygen, we've taken one from the carbon, we now have an electron deficient state. They have to form a second bond with each other to compensate for the loss of electrons, and thereby we have the alpha keto group that we need to allow interconversion of citric acid cycle intermediates with amino acids. Previously, we looked at the reaction catalyzed by aspartate aminotransferase. We saw that it doesn't just allow glutamate and alpha-ketoglutarate to be interconverted so that glutamate can enter the citric acid cycle, or so that alpha-ketoglutarate can be used to synthesize glutamate depending on our needs. But it also, in the same reaction, allows oxaloacetate and aspartate to be interconverted. This allows oxaloacetate to act as the exit point to make aspartate, and it allows an entry point for aspartate to enter the citric acid cycle as oxaloacetate. But notice that the only reason we can do either of these reactions is because we can swap the amino group and the carbon and the keto group with the other set of molecules. In other words, we can convert alpha-ketoglutarate to glutamate because we can take the amino group from aspartate and put it on alpha-ketoglutarate to make glutamate. But we can only take that amino group away from aspartate because that will generate oxaloacetate. Oxaloacetate can be used in the citric acid cycle. Conversely, we can only take the amino group away from glutamate and use oxaloacetate to make aspartate because oxaloacetate has the keto group in the alpha position that can be swapped for the amino group in the alpha position. So if we think about goal number 2, we can say that the oxidation of malate is needed to reproduce the alpha keto group that allows this interconversion to take place. Our third goal is to allow an electron deficient state in oxaloacetate that will enable it to bind to acetyl-CoA to initiate the next turn of the citric acid cycle. We've already seen the reaction on the screen several times now. The only thing that's different in this picture is that to emphasize this part of the reaction, the alpha keto group's oxygen atom is shown in red. We can trace that oxygen atom during the condensation of oxaloacetate to produce citral-CoA as follows. Because this carbon and this oxygen are electron deficient, they're hungry to bind with other things. That allows the carbon to bind to the CH3 on acetyl-CoA. That CH3 becomes CH2. The hydrogen and the electron travel down to the alpha keto group, still shown in red, in order to convert it to a hydroxyl group. That frees up a bonding site on this carbon to bind with this carbon. The top carboxyl group now becomes the middle carboxyl group. Had we not oxidized malate to oxaloacetate, this oxygen and this carbon would not be electron deficient and they wouldn't be able to accept the binding of acetyl-CoA to initiate the next turn of this citric acid cycle. So in summary, the last 3 reactions of the citric acid cycle allowed us to, number 1, add the third oxygen atom from water. Number 2, allow an alpha keto group to be reconstituted so we could swap oxaloacetate and aspartate back and forth with one another, which is needed to enable the swapping of alpha ketoglutarate and glutamate back and forth with one another. And number 3, it allowed us to create an electron deficient state in oxaloacetate so we can condense with acetyl-CoA for the next turn of the cycle. Now let's come back to look at this topic of using water to donate the oxygen atoms needed to release carbons as carbon dioxide. Shown on the screen is the stoichiometry of the citric acid cycle as shown in a standard textbook. The word stoichiometry comes from the Greek steichion, meaning element, and metron, meaning measure, to measure the elements. And what it means is we're accounting for all of the atoms by seeing how they rearrange in the reaction. And what stoichiometry is essentially quantitatively accounting for the reactions and products in any given reaction or set of reactions. And the stoichiometry of the citric acid cycle is typically presented shows 1 acetyl-CoA plus 3 NAD+, plus 1 FAD, plus 1 ADP, 1 inorganic phosphate, and 2 water, making 2 carbon dioxide, 3 NADH, 1 FADH2, 1 ATP, 2 hydrogen ions, and 1 free CoA. Now, what we're seeing here is the 2 water that are directly used in the citric acid cycle. What is behind the scenes here is that the third oxygen that we needed to release 2CO2 is also taken from water indirectly. And we don't see that here because we're not fully accounting for all of the atoms in this stoichiometry. We can see it more clearly shown in this diagram on the screen. The first water comes in during the hydrolysis of citral-CoA to form citrate. The first carbon dioxide leaves during the decarboxylation of isocitrate. The second leaves during the decarboxylation of alpha-ketoglutarate. The second water is used during ATP hydrolysis for some other totally unrelated reaction where we needed energy from ATP. The oxygen atom of that water is stored in the phosphate that gets added to succinyl-CoA to form succinyl phosphate. As phosphate leaves forming succinate, ATP is reformed, but the oxygen atom stays on succinate. So one water is irreversibly consumed for each conversion of succinyl phosphate to succinate. It's just that that water is consumed outside the context of the citric acid cycle, and so we don't typically account for it here. Succinate is oxidized to fumarate. During the hydration of fumarate to malate is where the third oxygen atom is donated by water. And then we oxidize malate to oxaloacetate, allowing the next turn of the cycle to go on. Although not clearly shown in this diagram, there's a principle hiding within this diagram that needs to be pointed out. And that's that when we donate the oxygen atoms into the citric acid cycle, we don't do so that they can directly generate CO2. We only donated one water when we got to citrate, and we released both CO2 before we added the second oxygen atom during the production of succinate, and before we added the third oxygen atom during the production of malate. This reflects a general principle that the atoms that enter the citric acid cycle during each turn of the cycle are not the atoms that leave during that turn of the cycle. In fact, this is even true of the carbons. Let's take a look at what happens to the carbons of the acetyl group from the very beginning of the citric acid cycle. The two carbons of the acetyl group and the one oxygen are shown in purple, and so during the formation of citrate, they constitute the two carbons at the bottom of the molecule. When we convert citrate to isocitrate, we move the hydroxyl group from the third position to the second position, and the carbons from the acetyl group are at the bottom, unaffected. The carboxyl group in the middle, shown in red, is the one that leaves in the next step. Neither the carbon nor the oxygen were added in the form of the acetyl group at that point. The acetyl group stays in the bottom two carbons of the molecule where it had been the entire time. Then we decarboxylate alpha-ketoglutarate. We don't release the bottom carboxyl group, we release the one on the top. This is the one that didn't come from the acetyl group. It had been there the whole time. And the two carbons on the bottom from the acetyl group stay on the bottom. So already we've released both carbon dioxide molecules, and neither of them came from the acetyl group. Now, if you look at succinyl-CoA, we're keeping track of the purple carbons from the acetyl group at the bottom until we get to succinate. And now we're not keeping track of them anymore. The reason is that succinate is the first completely symmetrical molecule of the citric acid cycle. It could be the case that the carboxyl group on the bottom of succinyl-CoA is the one on the bottom of succinate, but it could be the one on the top. If we flip succinate back and forth, it's not going to change anything because it's the same on one side as the other. So at this point, we can no longer say, well, this carbon came from this place, that carbon came from that place. We're not sure. Succinate then comes to fumarate, and fumarate comes to malate. And at this point, we have two carboxyl groups. One of them did come from the acetyl group. We just don't know which one. When we hydrate fumarate to form malate, and then we oxidize malate to form the alpha keto group of oxaloacetate, we can now start keeping track of this oxygen that came in from this water. And we can start keeping track of the carboxyl group on the top of the molecule, because now this molecule is no longer symmetrical. This red carboxyl group will be the carboxyl group that leaves as the first CO2 in the next turn of the cycle. And it may have come from the acetyl group that entered in the last turn of the cycle, or it may have been the acetyl group that came in even before that. We don't really know. The oxygen atom of the alpha keto group allows the condensation to take place. It becomes the hydroxyl group in the middle of citrate. It gets moved to the second position to isocitrate, and it becomes the alpha keto group of alpha ketoglutarate. That oxygen that came from the third water does eventually become a carboxyl group that will be released during the conversion of succinyl-CoA to succinate. But at that point, we only know that it will be released in a future turn of the cycle, because succinate is symmetrical and can be flipped back and forth. We don't know for sure whether it's going to be the next turn of the cycle or the one after that. All we know is that when we invest carbons and oxygen in the form of acetyl-CoA, we are investing them to be released as carbon dioxide at a later turn of the cycle and not at this turn of the cycle. And when we invest water, whether it's during the hydrolysis of citral-CoA or indirectly through the phosphate that forms succinyl phosphate, or during the hydration of fumarate to malate, we're adding that water to constitute carboxyl groups that will be released in later turns of the cycle as well. Now, remember this principle that water donates the oxygen to release carbon dioxide, and that oxygen is the limiting factor for the release of carbon dioxide for future lessons, because this is going to be super important when we come to talking about fat versus carbohydrate. The audio of this lesson was generously enhanced and post-processed by Bob Devodian of Torian Mixing, giving you strong sound and dependable quality. You can find more of his work at torianonlinemixing.com. To continue watching these lessons, you can find them on my YouTube channel at youtube.com/Chris Masterjohn, or on my Facebook page at facebook.com/Chris Masterjohn. Or you can sign up for MWM Pro to get early access to content, enhanced keyword searching, self-pacing tools, downloadable audio and transcripts, a rich array of hyperlinked further reading materials, and a community with a forum for each lesson. If you really want to own these lessons, study them, and get the most out of them, you can sign up for MWM Pro at chrismasterjohnphd.com/pro/PRO. All right, I hope you found this useful. Signing off, this is Chris Masterjohn of chrismasterjohnphd.com. You've been watching Masterclass with Masterjohn, and I will see you in the next lesson.